Swayam Prabha. Digital India. Educated India.
In the previous lecture, we considered fully developed flow heat transfer in circular tube or flow between parallel plates under variety of boundary conditions. Today, our interest is to move on to non-circular ducts. Non-circular ducts can be of regular shape such as rectangular duct or an annular sector duct, as we saw in the case of fully developed flow. But the ducts of this type can be solved exactly by the methods that were described there, because you get a Poisson equation of the type d2t dz square plus d2t dy square equal to u fully developed divided by alpha into dt bulk by dx. And u fully developed for a non-circular duct we have already obtained as a function of x and y, z and y. So, when you substitute for dt bulk by dx, you get a Poisson equation with a right hand side which is a function of x and y, and you can use Fourier series to solve such problems. The interest today, however, is very similar to what we saw in the lecture on fully developed flow in non-circular ducts. There we presented a method in which the method could be applied to ducts of arbitrary cross sections. We are going to extend that method now to include heat transfer. The whole purpose is to show that that method can be applied also to heat transfer, and with a very special provision, and that is the method can be applied to any arbitrary variation of thermal boundary condition along the circumference. So, for example, if I have a rectangular duct, I may have T w which is varying over the periphery, although actually the heat flux is constant. Q w is constant in the actual direction, but circumferentially T wall may vary or even Q wall may vary, or when we have a convective boundary condition, even the heat transfer coefficient H w on the outside of the duct can vary. So, we have three possibilities of T w varying, Q w varying or H w varying. T w varying situation arises principally when you may have a situation that a certain side of the duct is made of one material, where the other side is made of another material. That is one possibility. Q w variation can arise because you may have subjected to radiant heating, which can come from one side, and likewise heat transfer coefficient variation can also occur if there was a say flow over this duct, in which case the heat transfer coefficient would vary along the periphery, including there may be this can be purely convective heat transfer, or it can be H convection plus H radiation variation. So, both types are possible, and effectively you have H w. So, we want to be able to track quite a extensive ground today, in the sense we should be able to have a method which can which can be applied to ducts of arbitrary cross section and ducts that have arbitrary circumferential variation of the thermal boundary condition. Just to recall, let us look at how we solve the velocity problem for a duct of non-circular cross section. This was done in lecture 16, as you will recall, where we had the Poisson equation with a pressure gradient constant on the right hand side, and we defined a velocity u by that 1 over mu dp dx equal to u star minus z square plus y square by 4. And therefore, the Laplace equation turned out to be d2 u star zz square plus d2 u star dy square equal to 0, and u star b, the boundary value, was equal to where u is itself equal to 0 is z square zb square plus yb square divided by 4. And the solution to that we had shown is given by this expression, that u star is equal to I equal to 1 to n C I G I, but now I am calling it CUI to indicate that these coefficients were for the velocity problem, and GI functions were also given in lecture 16. N represents the number of boundary points you have chosen on the duct boundary. So, we will keep this in mind, that this is how we had solved the velocity problem. We now turn to solving the heat transfer problem. So, let us say again I have shown the duct of arbitrary cross section with duct boundary coordinate z b y b known, and again it is also a singly connected domain as before, but the q wall or t wall or even heat transfer coefficient along the boundary may vary. The governing equation will be d2t dz square plus d2t dy square u fully developed divided by alpha, the thermal diffusivity, into dt bulk by dx, and by overall heat balance you will see dt bulk by dx is a constant given by q wall bar dh by 4 rho u bar Cp, and q wall bar is the average constant heat flux along the axial distance. From the definition of friction factor multiplied by Reynolds number, we can readily represent u bar as 0.5 into 1 over mu dp dx dh square FRE, and the negative here implies that the dp dx is negative. So, that u bar is positive, and therefore, if I substitute for dt bulk by dx and u bar, then I would get d2t by dz square plus d2t by dy square equal to 8 FRE q wall bar by k dh cube, k is being the thermal conductivity, dh is the hydraulic diameter, multiplied by u over minus 1 over mu dp dx, and this quantity we defined as u star minus z square plus y square by 4 with this as a multiplier. If I take this to the left hand side, then and define theta equal to t into this quantity raised to minus 1, then the equation would simply read as d23 dz square plus d2 theta by dy square equal to CUI GI minus z square plus y square by 4. Here onwards, the treatment would get somewhat complicated. So, please be attentive in following the steps. So, I am now going to say let theta, the temperature, be equal to some theta star plus sigma I equal to 1 to n CUI, the velocity coefficients, multiplied by another function called GI minus Z4 plus Y4 divided by 48. This is a postulate. This is a postulate. Then you will see that substituting this into this equation would give me d2 theta by dz square plus d2 theta by dy square on the left hand side equal to the same thing in theta star plus cui into second derivative of gi functions with respect to z plus second derivative of gi functions with respect to y square in minus z square plus y square by 4. Now, suppose I say that this quantity, the second derivative of gi with respect to z and y, the sum of them is equal to small gi, then you will readily see that this quantity d2 theta star by dz square plus d2 theta star by dy square would turn out to be 0, because this is exactly equal to cui gi minus z square plus y square by 4. Okay. So, what I am going to do now is to substitute this equal to this or postulate that these functions gi are exactly equal to gi. So, if d2 gi by dz square plus d2 gi by dy square equal to gi, then for each gi I can generate a function gi and the solutions of that are given on the next slide. But the consequence is that, as I said in the previous slide, that it would mean d2 theta star by dz square plus d2 theta star by dy star equal to 0. Again I have a Laplace equation, and for the Laplace equation, as you recall, the solutions of x plus I y raised to n are all solutions of the Laplace equation for n varying from 0, 1, 2, 3, 4 up to anything, and we had taken n equal to 8 in the velocity problem. We will stick to that and let us see what happens. So, the solution would be as before, as in the velocity problem, the solution now would be a I g I, and theta would be a I g I plus c u I g I minus z square plus y square by 48. Okay. That is, if I substitute for theta star equal to a I small g I, is that right? The solution to a Laplace equation we had shown is a I g I. So, I have substituted that for theta star. So, this is theta equal to this term is theta star, and these are the additional functions with a velocity coefficient cui gi minus z to the 4 y to the 4 divided by 48. Now, of course, the coefficient a I we will show as we go along will be different when the boundary condition for T w is given, and therefore, those coefficients I have called C T w I. If the q wall varies circumferentially, the coefficient will be called C w I, and if V transfer coefficient varies, then the functions would be called C h w I. Okay. So, the A I here could take any of these three depending on the boundary conditions that we have. So, this is our solution to the temperature equation. Let us see how we can proceed further to develop a Nusselt number. But before I do that, here are the functions g I. So, g 1 is for n equal to 0, g 2 and g 3 are for n equal to 1, g 4 and g 5 are for n equal to 2, g 6 and g 7 are for n equal to 3, g 8 and g 9 are for n equal to 5, and so on and so forth. And you could verify very well with the small g functions that I have. So, basically in each case, if you wanted to see d2 g 1 by dz square plus d2 g 1 by dy square will give me essentially 0.25 into 2 plus 0.25 into 2 equal to 1, and that was precisely what g 1 was, if you will recall. And likewise, if I do d2 g by g 2 by dz square plus d 2 g 2 by dy square, then you will see this will become first of all 6z square plus 3y square plus 6z plus yeah, that is about it, divided by 12 and no sorry, this would be, so let us say dg2 by dz will be 3z square plus 3y square by 12 and d2g2 by dz square will be 6z divided by 12. Similarly, d2g2 dg2 by dy would be 6yz by 12 and d2g2 by dy square will be 6z by 12, and therefore, this quantity would turn out to be 6z plus 6z by 12 equal to z, and that is precisely was g 2, if you will recall from our lecture number 16. Likewise, you can check out all of them, and these are the 17 functions. The last 6 g 16 and g 17 are for n equal to 8. So, now let us begin to develop the solution for T w varies arbitrarily along this duct periphery. So, here theta w z b y b is specified. Then you will see from the solution that we have got, we simply substitute, we can get theta w equal to all these functions evaluated at z b y b, right hand side evaluated at z b y b, and that is what I have written here. So, you would get a I g I multiplied by c u I g I z b y b minus z b square plus y b square by 48. Now, as I said before, in this case a I will be taken as c t w I, then you will see that c t w I g I equal to 1 to n at z b y b would be equal to theta wall minus c u I into g I at z b y b and plus z b y b z b 4 plus y b 4 by 48, and the entire right hand side is now known at z b y b, because theta wall has been specified. G functions can be evaluated for z b y b, and c u I, the coefficients from the velocity problem, are also already known, and therefore, the entire right hand side can now be specified. So, essentially now you again have a problem very similar to that of the velocity problem. C t w I g I at z b y b is equal to some function of z b y b, some function of z b y b, and the task is to determine C t w I, which we will can do by LU decomposition as before. Next. So, in this equation then we determine C t w I by LU decomposition, and once C t w I are determined, I get the entire temperature solution as shown here. So, once C t w I are determined, then I would get the temperature solution. But to determine the Nusselt number at the wall, which will now vary along the periphery, because T w is varying along the periphery, it will vary, the heat flux would also vary along the periphery, because the wall temperature is varying. In fact, the heat flux would vary in a non-circular duct. Heat flux could vary along the periphery even when T w is constant, simply because the temperature profiles along the say I have a duct like this, even if T w was constant with respect to the periphery, the peripheral distance s, the velocity gradients and the temperature gradients can go on varying from point to point, and therefore, the heat flux itself would be the local heat flux would be varying along the periphery, although its integral value would remain same as that specified, which is the actually constant heat flux q wall bar. All right. So, let us evaluate then the temperature gradient at the wall. It would be equal to k by dt dn at the wall, where n is normal to the wall. So, q w, which is coming into the heat, coming into the duct, would be k times plus k times dt by dn at the wall, where n is normal to the boundary. And you will recall from your first course in mathematics that a normal derivative can be split into derivative along direction z and direction y multiplied by direction cosines L and m. So, I can write this as k L dt by dz plus m dt by dy at n. Basically, if you have that as the boundary and this is the n direction, then dt dn along this will be simply dt dz along the z direction, dt dy along the y direction, and dt dn would then be equal to L times dt dz plus m times dt dy, where L and m are direction cosines. All right. So, that is what we do here. So, you will see substituting those things here on the right hand side, and therefore, if I now switch t to theta through this transformation q wall bar, then I will get dh cube divided by 8 f r e divided by q wall bar. Remember, I had defined theta equal to, that was the definition of theta. That was the definition of theta, and that same thing I have substituted here to get dh cube 8 f r e q wall divided by q wall bar equal to d theta by dn equal to L d theta by dz plus m d theta by dy z b y b, and theta would now each derivative here would be L times C t w I d g I by dz plus C u I d g I by z at z b y b plus m times C t w I d g I by dy and C u I d g I by dy z b y b minus the L z cube plus m y b cube divided by 12. So, that would be the right hand side, which will enable me to evaluate q w, and I already know C t w I know d g I dy, I know g I function as well as small g I function, and therefore, the entire right hand side can be evaluated, and therefore, the heat flux variation along the periphery can be evaluated. The next task, of course, is to evaluate the bulk temperature u theta dx dy divided by u dx dy over the area of cross section of the duct. This is how we define the bulk temperature. And then the Nusselt number, which is q wall over T wall minus T bulk into dH by K, would be simply equal to this quantity into dH by K is equal to d theta by dN Z b y b dH theta wall minus theta bulk. And therefore, Nu this would Nu T w would be the will be varying along the duct periphery, and it is that quantity itself is very useful, but also useful is a quantity which is circumferentially averaged Nusselt number, and that is what I have defined in this equation, where S is a perimeter and the line integral of Nusselt number values along the periphery have been integrated with respect to perimeter. We now turn to the problem in which q w, the heat flux is varying in the circumferential direction. All right. The same temperature solution is to be used, but the coefficients CQWI are now to be evaluated. So, if I were to take QW equal to is specified, then the left hand side would become CWI L dGi by dz plus m dGi by dy at ZBYB equal to dH cube over this into Q wall bar or Q wall bar plus this minus CUI L dGi by dz plus m dGi by dy ZBYB, and all these quantities are known because Q wall ZBYB has been specified. Actually, uniform heat flux has also been specified, and all these functions can be evaluated, which I have called gamma ZBYB, and L dGi by dz plus m dGi by dy at ZBYB, if I were to call it as Fi, let us say, these are also known functions, then I would get again the velocity like problem CQWI Fi into at ZBYB equal to, therefore, CQWI can be determined by LU decomposition, and therefore, the solution would be C theta equal to CQWI GI, CUI from the velocity solution and this. So, I can readily evaluate theta W, and knowing this I can also evaluate theta bulk. Knowing theta wall, I can also evaluate theta wall bar as given, and of course, Q wall bar will be 1 over S line integral of Q wall ds. Then Nu for the Q wall varying would be given by that again as before, and the averaged circumferentially averaged heat transfer coefficient would be given by the expression that I have shown at the bottom of the slide. So, Nu cube bar QW is equal to dH cube at F Re dH by theta wall minus theta bulk, where theta wall is given here and theta bulk is to be evaluated in the usual manner. Now, I come to the very last boundary condition, that the heat transfer coefficient can be also be a function of circumference of the duct. So, in this case what would happen is what I have shown here. As you know, the definition of Q wall is K dt dN at ZBYB, and that would equal HW into T wall minus T infinity, where HW has been specified. HW has been specified, and T infinity is some temperature outside the duct which is known. Now, in this case AI would be HWI, and therefore, the solution would read as theta times CHWI GI plus CUI GI ZY minus this quantity. Theta wall would be simply that, and d theta by dN ZBYB HW over K theta wall minus theta infinity into CHWI L dGi by dZ m dGi by dy ZBYB plus CUI all this. This equation will now enable us to evaluate CHWI as I show. For example, this quantity would equal HW by K theta wall minus theta infinity minus the entire term on the bottom of the slide. So, you can see I can now say that if I define Fi equal to, it is simply L dGi by dz plus m dGi by dy HW GI ZBY. So, Fi is simply equal to what is given in the brackets. Then the right hand side would be all this, and the right hand side is known, the entire right hand side is known. So, again I get a equation which is I equal to 1 to n CHWI Fi equal to Z gamma times ZBYB, and therefore, I can evaluate CHWI from which I can get theta wall as well as q wall, because I can get d theta by d n. So, when the heat transfer coefficient has been specified, our main objective is to discover what will be the wall temperature and the local heat flux. The Nusselt number would of course follow from it, because H w is already known. So, now let me take few examples. You will recall that for this circular segment cross section, we had already developed the velocity solution, and therefore, the CUI coefficients are already known. Theta naught is the apex angle, and x is measured so and y is measured so. And I am going to develop solutions in this case for TW variation and QW variation along this circular segment. So, to begin with, what I have done, I have simply said that over the entire periphery of this duct, TW is constant. TW is constant. Of course, TW will vary with Z, dTW by dZ, I mean x will equal dt bulk by dx, because QW is constant. And therefore, the although the circumferential, which is a specific special case of arbitrary variation, dt wall by dx equal to dt bulk by dx, and therefore, actually T wall will increase with x, but circumferentially the temperature is constant. All it means is that the metal of the duct has very high heat, high thermal conductivity, so that any temperature variation is just evened out. And most of the solutions that are documented in literature are for this particular case of TW equal to constant, and I am going to take the case of theta equal to 90 degrees as a special case. Theta equal to 90 degrees, as you will recall, is nothing but the semicircle, very simple semicircle. So, have a look at this figure again. So, ZB, YBs are specified for all the boundaries 1, 2, 3, 4, 5, and what I have done now is only because of the symmetry from on both sides, I am only giving you solutions on the left side of the boundary, because the same solutions will be reproduced, because the circumferentially the wall temperature is constant. So, we expect symmetry about this y axis. So, I am giving you solutions only on the left hand side to save space on this slide. So, you will see minus 1, minus 0.99, minus 0.75, minus 0.5, minus 0.5, all these are on the negative side of Z, and so are these on the negative side of Z. And YB is equal to, given this is on the curved side top, and this is where YB is 0. The direction cosines are of course in each case the same, as turns out to be same, and the Q wall heat flux you will see is like this. Right at minus 1 0, which means this point, the heat flux is very small, very small. It goes on increasing as you go towards the top, as you can see here. 0 0 0 is the topmost, that is where it is 0.247. On the flat side, the heat transfer is 0.0207 minus 1. Again, on the flat side, again the heat flux is high here and goes on reducing. So, you have a high heat flux coming in here, high heat flux coming in here, and it reduces along the periphery in this direction and in this, and likewise on this side as well, which I have not shown by exploiting symmetry. And you will see how the Nusselt number varies, 0.023, 1.09, 4.24, and so on and so forth. Now, if I take a circumferential average of the Nusselt number that is shown in this column, it turns out to be 4.02 for the semicircular duct. This value matches very well with what is published in the literature, in which the solution has been obtained by Fourier series, and that is possible for this elegant case of a relatively regular shape of theta equal to 90. Even the finite difference solution for this problem gives you very good agreement with this value. So, now what I want to show is how were the coefficients CTWI, these are the CTWI coefficients appear for TW equal to constant, and this was the case of 90 degrees that we had earlier considered, semicircular cross section. This is the case of 60 degrees, this is the case of 45 degrees. This is okay. Now, you will see C1, C2 are 0 or CTW1, CTW2 are 0, C3 is finite, C4 is finite, 5, 6 are 0, 7 and 8 are finite, 9 and 10 are 0, 11 and 12 are finite, and 13, 14 are 0, and 15, 16 are finite, and so is 17, although very small as you can see here. In each case, the circumferentially average wall Nusselt number has also been calculated, and as you can see, as the angle becomes smaller, the Nusselt number goes on decreasing. Of course, this Nusselt number is based on hydraulic diameter. So, 4.02 is at 90 that we saw, 3.90, 3.79, 3.66, 3.04 at 10 degrees. Now, let us turn our attention to the case in which circumferentially Q wall is specified, and again in this case it is Q wall is constant along the circumference. So, basically it is QW is uniform around the circumference. Again, I have considered uniform simply because it is a case of it is a case in which some published solutions are available. So, again exploiting symmetry, I am giving results for, in this case, not 90 degrees, but 60 degrees, just to make some change. I am considering the case of theta equal to 60 degrees, and these are the points on the curved boundary, and these are the points on the flat boundary. This is the L and M, and now you can see what the wall temperature looks like. The wall temperature is 0.237 minus 2 at point 1, which is the point over here, TW, and it is the highest value. It is the highest value, as you can see from the table, that 237 e to the minus 2 is the highest temperature, and then the temperature goes on reducing as you move towards the top of the duct and along the flat sides toward the center of the duct. This represents a hot spot. The bulk temperature in this case was 0.0012. So, you can see how big this is. This is 1.22 raised to minus 4, whereas T wall is this. It is to discover such hot spots that solutions of this type are very important, because circumferentially, although the heat flux is uniform, wall temperature can vary and you can get hot spots at corner points. This is of great consequence, both for example, if your the corner point also is a highly stressed point, and if it has very high temperature with very large temperature gradients around that point, there could be cracking or thermal warping or anything of that kind can happen. So, solutions of this type are essentially meant to discover hot spots along the wall. As you can see here, at all the points that I have shown, those points close to the corner are very high temperature. If you look at Nusselt number now, it is 0.67 and it goes on increasing to 37.5, but look at this value of 0, 0, 0 right at the center on the flat surface. You will see 0, 0, 0, y equal to 0, x equal to 0 means that temperature, and you will see that at that point the Nusselt number is negative, because T wall is 0 and it is less than T bulk. So, essentially all it implies is does not mean negative heat transfer, but simply the wall temperature is much lower than the bulk temperature, resulting into a negative Nusselt number. Then again it picks T wall becomes greater than. So, such things can also happen, that a wall temperature actually goes below the bulk temperature, 4.84 and 0.619 again. So, in this particular case, Nu bar is 1.657 for 60 degrees. It is 1.6, which is the circumferentially averaged heat transfer coefficient. Again, I have shown on this table what the coefficients are for Q wall equal to constant condition. And you can see again C3, C4 are finite, C7, C8, C11, C12, C15, C16 and C17. These are the coefficients, same as before for constant wall temperature, they are finite, remainder are 0. And you can see for theta equal to 90, it is the circumferentially average heat transfer coefficient is 2.78, 1.61, 1.03, 0.433, and for a very narrow angle it is 0.4049. You will see that the Nu Q wall bar is less than Nu T wall for all angles. Remember, we had 4.0 T 2 here, 3.90 something here, and so on and so forth. So, now these values have been verified by finite difference calculations also. So, this is a very convenient way of developing solutions for uniform. Now, of course, just to remind you, I have taken circumferentially uniform wall temperature and circumferentially uniform heat flux just as special cases, but you could well have any arbitrary variation of Tw and Qw, and still we would get the solutions exactly in the manner I have described. I will now take a new kind of a duct for which we had earlier not obtained velocity solutions, but it is simply a duct in which the unrounded side is 2a along the x direction and 2b along the y direction. So, I have chosen 14 points. B is radius of the rounded side and 2a is the long side. Now, you will appreciate if B was equal to A, you will get a perfect circular duct, and what my interest is to show you that when B is equal to A, in fact, you generate the circular tube solution that we are all very familiar with. So, here is for different B by A, I am showing you the values of Cu, because these were not shown earlier, because I had not obtained the velocity solution earlier, but here is something that is shown, and you will see that only 1, 4, 8 and 12 are finite. So, for 0.25 I get 19.78 as the friction factor and Reynolds-Number product, 0.5 I get 17.23, and 1, as I said, is a circle or a circular duct for which only Cu1 is finite and it is Fr is equal to 16. So, although this is a limiting case of the geometry that I have shown, it does predict quite accurately the circular tube value. For the same cases, I have considered the heat transfer under constant wall under uniform wall temperature around the duct, and again you find CT1, CT4, CT8 and CT12 are finite for all of them, and you can see this is 5.944, 4.73, and for B by A equal to 1, which is a circle, you will see only CT1 and CT8 are finite, and you get a value of 4.367. Remember, for a circular duct, when QW is uniform, TW is also uniform for a circular duct, and that is what is shown here. So, for a circular duct, that is B by A equal to 1, you get 4.367 as NUT wall bar, and the same value is predicted also by specifying constant heat flux as that, and the coefficients turn out to be the same. And you will see that the coefficients in constant T wall case is CT1 is finite, CT8 is finite, but in constant heat flux case only CQ8 is finite. Now, interesting case is that of 0.25, B by A equal to 0.25, and I have mean Nusselt number as minus 15.46. All it means is that although the heat flux is finite on the wall and it is coming in, TW bar, the average TW bar is less than T bulk, and therefore, you have negative Nusselt number. Such things can happen. Such thing can certainly happen in case of non-circular ducts. You will recall that I had obtained finite difference solution to a circumferentially varying boundary condition of the heat flux along the circular tube. Yes, Q wall equal to A times 1 plus B cos theta was the circumferentially varying heat flux, and had obtained solutions by finite difference method. Those solutions I have now obtained by the present method. Next. So, you will see here I have taken Q wall equal to Q wall bar plus 1 plus A cos theta. Q wall bar has been specified here as 0.0625, and you can see how the heat flux variation varies here, and how the Nusselt number varies, exact values as calculated from that formula that I had given there, and how the presently computed values, absolute agreement for when A is 0.2. When A is equal to 0.5, again there is a very good agreement, except at this point where the value here predicted is somewhat, because of rounding off, it has been printed as minus 24, but actually it is minus 23.9, and the solution has been very well reproduced by the new method. So, solutions for circumferential variation of HW are not given here. This is left as an exercise that will require writing a general computer program with LU decomposition. Of course, as I said, this method is extremely versatile. All you need to do is write a general computer program with small g functions and big G functions, and a routine that will evaluate U bar and theta bulk. And all you do then is to have an input subroutine in which you give boundary coordinates and specify whether you want to solve for TW, QW and HW. So, a general computer program can be written, and therefore, this method turns out to be very this is particularly of great importance, because we nowadays have microtubes in which all kinds of complex cross sections, such as the moon shaped duct that I had mentioned in my earlier lectures, or sinusoidal duct, these sort of ducts come about, and therefore, this method is very valuable, and in microtubes you invariably get laminar flow. So, in the next lecture we shall consider developing heat transfer solutions.